Okay, greetings. Matt Roscoe here, Math 133, Geometry for Elementary School Teachers. We're going to talk a little bit today about shearing. This is section 12.5, changing shapes without changing area. So what are we about today? So we'll explore what is shearing and through a series of pictures, and then I have an applet where you can actually look at what's happening in an interactive sense, and then we'll formally state Cavalieri's principle. We'll talk about its implications for shearing triangles and shearing parallelograms, and then we'll address the misconception about shearing versus squashing and leave you with a classroom question. So the following pictures show 4 different figures. Actually, it's 5 different figures, I think, that are made of using 27 stir sticks. What can we say about the areas of the figures? Are the areas the same? Are they different? And explain. So here's a picture of the 27 stir sticks stacked up to make, looks like a rectangle. Notice that the stir sticks are side by side, lined up, none are on top of one another or overlaying one another. So then in the next picture, what I've done is I've just pushed the 27 stir sticks to the left using a ruler to make them line up nicely, and I created what looks to be a parallelogram. And the question is does the area change getting from here to here? And why or why not? So what if then I got creative and I said, well, what about just going the other direction? What if I took these 27 and I pushed them the other direction and I got this parallelogram? Would the area be the same or different, and why or why not? I hope you're formulating the question in your mind as you think about this. So what if I got fancy and I took a bite out of one side? Well, not took a bite, but I used a cup and I pushed the stir stick so that on one side we have the radius of a circle sort of looking thing, and then on the other side we have kind of those parts moving respectively to the hole, I guess, I've created on the right. So what do you think? Would the area be the same or different from this one and this one and this one, or would this guy somehow have added or subtracted area from the others? Lastly, what if I made sort of a dart-shaped thing with the 27 stir sticks by pushing the corner of a book into one side and creating this thing that looks sort of like an arrow? So hopefully what you thought is that the area isn't changing here. The reason that it's not changing is I have 27 stir sticks, right? Each one can be thought of as a little length times width rectangle. And since I've neither added nor subtracted any stir sticks in creating the 5 different figures, the area is the same because the sum of the little strips of area hasn't changed any. So we kind of think of shearing as adding little strips of area. Those little strips can be thought of as little rectangles or as small or as thin as we like them to. So they're approaching this idea of little horizontal lines that are all stacked on one another. So let's take a look at the shearing applet. In the PDF of this presentation, you can just click on that button and it should take you then to this picture or this applet, which I created for our investigation. So I've got a triangle, and what I'm going to take a look at is manipulating points A, B, C, and D to see what properties are true about shearing. So if I take A and try to move it, I can't move it up or down, but I can move it side to side. And what I notice when I move it side to side is that the area of triangle ABC written up here doesn't change. So in other words, a triangle sheared left or right, that is, I guess it's no surprise really that this happens because of course the height is maintained the same and the base is maintained in the same length, so height times base times 1/2 should give us the same area. Maybe if I move this into 4, I can see now I have an area of 10 units because this is a 4 base of width 4 and a height of 5, so 4 times 5 is 20 divided by 2 is 10. Makes sense that this guy has an area of 10. Of course, this guy will have an area of 10 as well. This triangle being right will have an area of 10, 4 times 5 divided by 2. But all of these acute triangles in here also will have area 10. This one will have area 10, another right triangle, another obtuse triangle. So all of these have area 10. And the reason they all have area 10 is because the height and the base isn't changing. But here's what's really interesting, I think, about shearing is that not only not only do we have, I guess, the logic that areas are the same for triangles of equal height and base, but all of the segments of sheared triangles that are parallel to the base that connect one side to the other also maintain their length. So take a look at DE, this pink segment. You can see that the length of segment DE is 1.64 units, but that length maintains for any one of these triangles as A sweeps across this line parallel to its base. And so we can kind of think of DE as a swivel, I should say a stir stick, like in the first pictures. It's a stick, of a certain length, and on top of it there's one that's a little shorter, and on below it there's one that's a little longer. But if we move it, any one of these will maintain its length. So 2.46 units there for DE for any of these triangles that are sheared versions of one another. If I move it down even farther, of course, it'll be even bigger, but that length of that stir stick, if we want to think of it that way, maintains. So that's really what's going on in shearing, is that we sort of think of a figure as being a whole bunch of stir sticks stacked one on top of the other, and that it doesn't matter where we move those stir sticks so long as we move them in a sense parallel to the base, they will all maintain their lengths. So I hope you have fun playing with the applet. I would highly suggest you do so. I'll go ahead and pause it and go back to our presentation and go on to our next slide. So what is Cavalieri's principle? It says that when a shape is sheared by moving every point a fixed distance along a line parallel to the base, which is fixed, then the original and sheared shapes are equal in area. So it's moving stir sticks, if you like. So what does that mean for triangles? Well, that means that if I take a triangle with a certain base and a certain height, that I can shear it, and shearing it in any direction will allow me to create triangles of equal area. So, for example, if you get an obtuse triangle, of a certain length, then let me get rid of that. You can think of it as being the same area as its sheared right triangle. So, in other words, if I moved this guy over to here, to this point right here, then that right triangle, this one over here, would have the same area as the obtuse triangle. So I can move a vertex parallel to its base in any direction and still achieve a triangle of equal area. Another thing that's interesting is that the segments are all the same. So for example, this segment is 2 units in length. Well, it turns out that if you measured this segment right here, it would also be 2 units in length. And if you measured this segment right here, it would be 2 units in length. So the horizontal segments also maintain their size as we shear a triangle. It's even more, I think, important to understand shearing when we think of parallelograms. Anytime I have a parallelogram, then I can shear it and maintain area. And this is kind of easier to see because of perhaps the additivity and moving principles, but certainly this parallelogram and its accompanying rectangle or sheared rectangle are equal in area. If we cut this little triangle out of this left-hand side and put it over here, of course, we'd achieve that rectangle. But we can also think of it as having, lines or swivel sticks that have been, stir sticks that have been sheared or moved in a sense parallel to the base. Notice that one thing that's really important is that the height doesn't change in shearing. So the figure is elongated in the sense that this side grows in length. So the slant height, if you'd like to call it that, slant height grows in length. But the overall altitude of the rectangle or parallelogram remains the same. So I want to make you completely clear that there is this misconception about shearing and squashing. So we think of this as a good picture of what shearing means. So we have a certain number of here we have toothpicks, and we can align them in a different way. So more like a parallelogram here, and we can think that, okay, this and this would have the same area because we haven't added or subtracted any toothpicks to the diagram. So one of the things to check in shearing is, do I have the same base and the same height? And it does appear that I have the same base length and the same height length. So indeed, this is a case of shearing. Squashing is often confused with shearing. Here I do maintain the same base, so the base is the same here and here. But what's happened is I've lost some height. Does everybody see that this height is much taller than this height? So when I have fixed sides and I just simply squash it, so this picture is meant to be straws that have a I guess a string inserted through them and tied. So when I have fixed side lengths and I squash, then actually what happens here is I lose area, right? Because some height is now missing from the figure. So shearing is maintaining, the height, and here squashing is not. So make sure that you understand the difference between shearing and squashing. Okay, well, let me end by talking about a classroom question. So Nick notices an interesting property from some of the triangles drawn in the figure. Can you guess what Nick noticed? So here's a figure. Maybe we would think of it as a logo for a company or something like that. Do you notice the interesting property that some of these triangles have? And how could you talk to Nick about why that property is indeed true? Okay, we'll talk about that as I guess, to bring our investigation of shearing to a close on Monday when I return to the classroom. I hope you have a nice weekend, and I'll see you all on Monday.